Okay, so first of all,
oh yeah, sorry.
Yeah.
Okay.
Okay, so thank you very much for the invitation to speak here.
Sure.
So yeah, I'll talk about renormalized Witten-Reshetikhin-Turaev invariants and M traces, which somehow come from the superquantum group UQSLMN at root of unity. And from the beginning, I want to mention that all this work, it's a joint work with Nathan Geer and Patureau. So I'll start with the outline of what I'll speak today. So the first part will be a bit of the categorical setting about pre-modular categories, so that we know what we look for. And then in the second part, we will somehow see the algebraic setting, which means the representation theory of this superquantum group at root of unity, and what we will use from that. And then there are two main parts. So the first part concerns the projective representations of this superquantum group and how we use them in order to produce a nice category which gives extended ETQFTs. In the last part, we will use another idea of modules which come from the perturbative modules. And then from that, we'll see that we can get a nice category which gives us symmetric invariance. So that's the plan. And I will start just with the motivation. So the idea is to construct symmetrical invariant ETQFTs from the representation of theory of this superquantum group. And somehow historically, there are this kind of, from the representation theory point of view, we have quantum groups and then we have superquantum groups. And now, for example, on the categorical setting, we have the notion of modular categories. And then this notion of modular categories was used by Reshitikhin-Turaev in order to produce Witten-Reshetikhin-Turaev invariants. And somehow they obtain modular categories from the representation theory of UQSL2 at root of unity. Okay, so that was in the 90s. And now the idea is to go towards superquantum groups. And now when you go to superquantum groups, you have a very rich representation theory. And then this categorical setting was developed and Blanchet, Costantino, Geer and Patureau showed that you can use relative pre-modular categories in order to obtain three-manifold invariants and with some extra conditions TQFTs. And if you are really modular, then Marco de Renzi showed that you can get TQFTs and extended TQFTs. So the basic idea is that for a modular category, you want to have a finite number of simple modules such that you can your category is semi-simple with respect to those. And the idea of putting the word relative is that you will add a grading and you will slice your category such that each slice will be on its own somehow semi-simple with respect to a finite number of simples. But then overall, your category might be very, very rich. So this is why you put this grading. So what I'll show today is that we'll look at the representation theory of UQSLMN at root of unity. And then the perturbative representations will give us a relative pre-modular category. And then the projective case will give really a modular one, relative modular one. So that's basically the idea. Okay, so now I will state the results which we will get to. So the first theorem tells us that the category D of projective representations of of the unrolled quantum group at root of unity associated to SLMN is a relative modular category. And so if you plug in the machinery that Marco de Renzi constructed, then you get an extended QFT. That's the first idea. And then somehow on a separate direction, we will construct something from perturbative representations. So more precisely, we will construct a quotient with respect to some negligible morphism of a subcategory of perturbatives. And show that that is a relative premodular category. And for the particular case of SL21, we will show that that relative pre-modular category, it's in fact non-degenerate. So if you plug in the machinery constructed by Geer, Patureau, and Costantino, you get manifold invariants. And then we conjecture that somehow this property holds for or SLMN, but we prove just for SL21 for the moment. Okay, so that's the plan. And now I'll start the first part of the talk, which is about the categorical setting. So it's categorical setting that is needed in order to obtain invariance. And so now I'll start to discuss about pre-modular categories. So let's say that we start with a ribbon category. And then I will start to list which requirements we have in order to get a pre-modular category. So now an ideal in this category means a full subcategory, which is stable by regex and then which absorbs the tensor product. And an M trace on an ideal means that basically you have for each object V of I, you have a family of you have a morphism TV from the endomorphism of this V towards the ground ring, such that you have two properties. So you want cyclicity, namely that if you take a morphism F and then a morphism G, if you compose them in one way, and then you evaluate for the first trace, it's the same thing as composing them in the other order, and then closing up and evaluating the corresponding trace. Yeah, so that's usually the property of traces. But now you want also a partial trace property. More precisely, if you have an endomorphism of a tensor product, and then you just close it to the trace corresponding to the tensor product, that's the same thing as taking your endomorphism, first close it with a usual partial trace, and then you will obtain an endomorphism of the first object, U, and then you close with this trace to U. Okay, so it's basically the property that you can, if you have two strands, you can just put one inside if you put the partial trace. Okay, and once you have an M trace, what you can do is to define so-called modified dimension, which is just the evaluation of the trace on the identity of the object. Okay, so that's one piece of data. And now another definition that we need, it's a notion of a completely reduced dominating set. So basically, this tells us that we want a set of objects, Vi, in our category, such that the dimension of the home space between two different objects is 0. And then we can describe any object from our category or the identity of that object as the sum of compositions of morphisms which go towards and from these special objects here. Okay, so we factor the identity as a sum of compositions through this set of objects.
Cristina, does I have to be finite?
No, for the moment, no.
Okay.
No. Right. And now, so the second piece of data that we will need, it's called a free realization. Oops, sorry. A free realization of a commutative group, which means that we will fix a set of objects which is parameterized by that group, such that you have good properties, basically. And one of the good properties is that when you take the tensor product, then it's exactly what you associate to the sum of the elements of the group. Okay, and other good properties which are quite natural. And now a third piece of data, it's a grading. So this is the idea of taking our category and slices it into pieces. And then we'll see what we require on each piece. So the grading means that you fix a commutative group, and then you want that you slice this your category C as a direct sum of CGs, where G is free to go in the group G, such that, and then here we have the picture. So we imagine that here is G, here is C. Yeah, you slice it into bits. And now what you require is that the identity it's in C0. Now, if an object is in CG, then its dual is in C minus G. So it's symmetric with respect to that. Another thing that you require is that for different pieces, you do not have home spaces. Okay. And the last part is that if you have V into the grading G and W into grading G prime, the tensor product sits in the sum of the gradings. Okay, so that's the definition of the C grading. And now finally we can define what is a relative premodular category. So the input is the following thing. So you have to have a linear ribbon category. And then on this category C, you want a grading by a group G. You allow yourself to have a small set. Okay, small set means that basically it's symmetric, and then you cannot cover your whole group by translations. And you want a free realization Z. But you want your free realization to go in the grading 0 of your category. Okay. And so now, if you have this piece of data, you call C to be a premodular G category relative to Z and X. If you have two properties, so the first property concerns semi-simplicity. Namely that for each grading which is not in the small set X, when you look at your slice of the category CG, that in that CG you can find a finite set of simple objects, such that if you move this finite set by the free realization, by testing them with free realization, then that gives you a completely reduced dominating set. Okay, so basically everything from that piece can be described from direct sums of guys like this. Okay, and now the second condition is a compatibility condition, which concerns the braiding. So you want a map psi from G times Z with values in K star, such that if you take, so here C is a braiding which is associated to sigma of K and B. So if you compose a braiding twice, that's actually a multiple of identity. And that multiple, it's given by this function psi. Okay. So these are the requirements for a premodular category. And now, in order to get to modular categories, you need extra requirements. And for this, I'll just briefly recall what is a Kirby color. So we said that the Kirby color of index H, it's a linear combination of the special elements which correspond to the piece IH. So which was that finite set of simples, weighted by their modified dimensions. Okay, so that's omega H. And now a relative modular category. It's a premodular one for which there exists a modularity parameter psi, such that we have these properties. So for any two gradings which are not in the bed set X, basically, and for any indices of simples in G, you have this diagrammatic calculus. So this diagrammatic calculus means that you want to be true when you apply the Reshitikhin-Turaev construction. Okay, and you want this psi to be non-zero. Okay, and now I'll start the second part, which concerns the super quantum group that we work with, and then in the third and fourth part, we'll see how we can construct such categories from this representation theory.
So Cristina, just to stop you, so this this condition about where you dBi and then this curvy color, this is precisely rigged up so you get a 3-manifold invariant?
Exactly, yes. Yes. And also I think the ETQFT.
And the TQFT, okay.
Yes.
Okay, thanks.
Yeah, you're welcome. So I think for 3-manifold invariants, I think there is another condition which I didn't say actually, which is a non-degeneracy. And for 3-manifold invariant, you need the non-degeneracy. But somehow for TQFTs and TQFTs, you need this more modularity condition. Okay. Right. So then I'll start the theory about the superquantum group at roots of unity. So this will be also split into subsections. So first I'll say which is Hopf algebra that we work with. So that is a super Hopf algebra associated to SLMN. Now, every time when I say super, I mean that we have a Z2 grading, and then everything will have to be compatible with respect to this Z2 grading. Okay, and then we start with M and N natural numbers, which are different. And then a very important parameter for us will be R, which is M plus N minus 1. And we consider L to be greater than R, odd, and we will work at the L's root of unity, and denoted by Xi. And now, so I want to say which is unrolled. So we'll work with the unrolled quantum group. Okay, denoted by U Xi H. And then this unrolled quantum group has four main generators: EI, Fi, Ki, and then Hi. Okay, with many relations, which I'll not write it down here. They involve somehow the things which are described the algebra element, the Lie algebra element. Okay, but what I want you to take out of here is that it's a C superalgebra coming from UQSLMN with generic Q, but when you put Q to be a root of unity. And here we added these extra generators Hi, and this is an unrolled part of the quantum group. And with the Z2 grading means that all generators will be even, except the EM and FM, which will be odd. And so here I'll just say a few words about the SLMN part. So this is the special super Lie algebra of Mn times Mn matrices, where the super trace with respect to the M and N is 0. Okay, and then you can describe it in terms of generators. And the idea is that basically for the relations, you will need the Cartan matrix, which is given by something like this, and then you will need a vector with R component, D, so A and D. And now what will be used in the construction is a symmetric non-degenerate form on the Cartan subalgebra. So you have a form from H tensor H towards C, and then you have the induced form on the dual. And then here I just wrote the main relations that you have. Okay, so the form on Hi and the Hj, it's somehow encoded by this D and the A. And then we will also work with simple roots, which will be parameterized by R, numbers from 1 to R. And then this set of simple roots will give root lattice. Okay, and then for the simple roots, so simple roots are elements of H star. And then you have this somehow this description, how a root is evaluated on a vector H. Yeah, and also you have also weights which are basically element of H star with this condition. Okay, so basically this is somehow the main point that I'll say about this algebraic setup. And now I want to say that now this UCG, from now on I'll say UCG, it's a Hopf superalgebra. And what we'll use, it's related to its representations. And we'll look at its weight modules. And then we will go deeper and deeper and use somehow nice modules out of this set of weight modules. So a weight module means that you have a representation of this U psi j, such that all hi act diagonally. And then ki acts as a power of hi. Okay, and then this power somehow uses that special vector d. Okay, so these are the weight modules, and then d, it's for us will be the category of weight modules over this superquantum group. And now we have a picture with what happens with weight modules. So, for example, if we look at the finite dimensional U psi j modules, then this will be basically parameterized by this H star, which is CR, and then we can see it as CR minus 1 times C. We'll always split like this. And the correspondence is that, so this is a proposition, which tells us that the correspondence is V lambda has a unique highest weight lambda. And that's one we want in the correspondence. And this will give us a rich family of representations. So C to the R. And now I want to say that somehow there is an interesting part of representations which come from representations at the generic parameter. Namely, if you look at the finite dimensional weight modules over UHG with the H-adic version of the quantum group. I mean, I will not enter into details, but I just want to say it's a quantum group which is not at root of unity. Okay. The idea is that if you don't take a root of unity, then the representations are indexed by z to the power r minus 1 times c.
Sorry, Cristina. So UQH is that's the unrolled quantum group. U sub H is just the super quantum group for, and we should think of it as at a generic.
Yeah, it's over C of H.
Okay.
So it's
okay. That's what the H means. Okay, fine.
Okay. So it's a H-adic version. Yeah. Yeah. So there is at non-roots of unity, somehow you have less representations. So you have this and these representations are somehow in correspondence with this set. And now we will call this set the set of perturbative weights. And we should think of them as somehow big representations which come from representations over the generic version. Okay, so this is one thing that we will use. So in some sense, we see that when you put the root of unity, we have more representations. And another set that will be important for us, it's a set of typical modules. I'll say in a moment what it is. And then the set of typical weights correspondingly. Okay, so now the formal definition is that a weight is called perturbative if its evaluation on HI all I different than M, it's in Z. And a representation is perturbative if all the weights are perturbative. Okay, and then so D was the category of all weight modules, and then we can restrict on the category of perturbatives. Okay, and that's DP for us. Okay, and then so the correspondence is that H star, it's basically somehow isomorphic with C to the R, split it like this. And then a weight, lambda, will be parameterized by the complex part, CR minus 1, and then the just one C here. And now there is a description. I will not enter into all the details about typical weights, but I just want to say a characterization which tells you when a weight is typical. And then we'll have later statements which tell us that typical weights somehow help us and they're easy to understand from the tensor product and the compositions point of view. So typical weights means that lambda AC is typical if and only if we have this condition. So basically lambda AC is parameterized by a vector with R components, and then you want that if you sum up bits of those components, you don't want to arrive into L over 2Z for various ways of splitting this vector. Okay. Right, and then in this fashion, what you can do is to fix the part which is in CR minus 1, so the C component of the weight, and then look at the set where lambda AC is typical.
All right, Cristina, just one question. So it's L over 2Z, where L was the order of the root of unity?
Exactly, yes, yes, yeah. Yeah, so now the idea is that so we should think of the set of weights as C to the R, and then we can think of it in 2 dimensions, okay? And the idea is that if you fix this part, which is in the CR minus 1, then you have something which is parameterized by C. And you denote by this C with 2 dots, the part where you get typical weights. And there is a proposition which tells us that this set is a dense open set in C. Okay, so we have a lot of typicals. And yeah, so that's a picture which we will use at some point. And so the idea is that we have typical perturbatives and then all of them. And now I'll start the part where we use all of them. And then in the fourth part, we will restrict to perturbatives and construct from there. Okay, so what we want is to construct a relative modular category from projective modules in D. Okay, and D was the category of weight modules. Okay, and now in order to prove that it's relative modular, we have to basically show 5 main points. So we need the ribbon structure, we need the gradings, which means the grading by the group and then the realization of another group. We need a trace, and then the 2 requirements are the pre-modular property and then the modularity condition. Okay, and now I start to discuss a tiny bit about the ribbon structure. Okay, so now this D is a Brady category with a family of Gradings CVW, where this CVW, it's defined in the following way. So the braiding, it has a twisting part, but I just want to mention that in this context, the twisting part, it's more subtle than the usual one. Namely, it encodes the sign, so that's the grading. Okay, and then the a part arc psi, which is somehow comes from a truncated version of the usual R matrix. So take the R matrix over the quantum group with Q parameter, and then you truncate it and show that you have something which has the good properties. And then that will give you the braiding for D. Okay. So we have the braiding, and then we need the dualities and twist. Now, another property that that you can do is to construct a pivotal element. And in order to construct a pivotal element, the idea is to start with a particular element here. So here, rho is half of the sum of the roots, and then rho 0 it's half of this of the sum of roots corresponding to the 0 part. Okay, and then you look at this element pi, and then to this element we will have an element in UXCH of G, which is k pi. And now this k pi it's a pivotal element, meaning that if you look at the S square of of U, that equals with k pi U k pi minus 1 for all U. Okay. Right, so we have a pivotal element, and now with this pivotal element, we can define dualities. Okay, and then for defining dualities, so we do this really in the usual way. So the evaluation and then co-evaluation to the left are just the usual ones. Okay, so the usual evaluation and the usual co-evaluation is VI times VI star. And now the part to the right is different. So the part to the right, so evaluation, which goes from V to V star towards 1, is defined in the following way. So you start with Vj and then Vi star, and then you go to so you evaluate Vi star on the Vj where you act with k pi. So you twist with k pi, which is usually what you do. And then you also add the sign. So this sign comes from the super part. And for the co-evaluation, the same. So it's a usual thing that you send 1 to VI star and then you twist with k pi minus 1, but then you correct it with the sign as well. Okay, and then you have this set of dualities, and then you look at the right partial trace of the braiding, which usually means that you want to have a twist. Okay, and now there is a theorem which tells you that this trace of the braiding, it's indeed a twist, which means that it is compatible with the braiding, and then D, it's indeed the ribbon category. So these are all things that need to be checked. Okay, but it, yeah, I mean, it works, and then you have this first piece of data. And now the second part is that we want to grade everything. Okay, and now in order to grade, we will use the root lattice lambda r, and then the group that we'll use, it's H star factored by lambda r. That's G, and then Z, it's Z2 times Z to the r. That is for the free realization part. Okay, so first of all, what we have to do is to grade the category by G. And now, if we take a class of lambda in G, we define D lambda to be the supermodulus with all weights of the form lambda plus alpha, where alpha it's in the root lattice. Okay, so we allow to vary just in the root lattice. And another thing that we need, it's a free realization. So if you take Z to be Z bar and lambda, where Z bar it's 1 or 0, and lambda it's in Z to the R. Yeah, we want to construct a module, sigma of Z, and that module it's basically just one-dimensional, with the grading given by Z bar. Okay, and then the E action, F action trivial, and the H will act, the H action will be prescribed by lambda in this way. So H will act as the identity times the evolution of lambda on H. Yeah. So lambda basically it prescribes the weight.
And the Z0 bar, does that come, that doesn't play a role here?
Yeah. I mean, this bar tells you the if it's even or odd. You need a grading.
Okay.
So you want a one-dimensional module which is graded.
Mm-hmm. I see. Oh, I see. It just tells you which degree, which Z2 degree it's at. Okay.
Exactly. Yeah. Mm-hmm. Yeah. So basically, the two part comes from the super part. Okay. So that's a grading and a serialization. And yeah, so the idea is that we need a trace, an M trace. And the theorem tells us that it exists up to a scalar, a unique M trace on projectives of D. Okay. And that's somehow based on a work of Nathan and Bertrand on general somehow traces on projective modules. Okay, so that's the theorem which tells us that we have a trace. And for the pre-modular property, the idea is that basically you can construct by hand and by studying somehow these representations a small symmetric subset in G, such that if you are away from that subset, d lambda is semi-simple, and it has a completely reduced dominating set. And that was somehow a requirement that you wanted. That was part of the semi-simplicity requirement. And the second lemma is that you have you can take the bilinear map psi given by this formula. So psi of a class of mu, so a class of root, and then z bar lambda, basically just ignores the z bar, and then it takes the product of mu and lambda. And you put psi to the product of mu and lambda, and that will satisfy the compatibility condition. Okay, so overall, if you put all of this together, you get a pre-modular condition. And now the only thing that you have to do is to check the modular condition, so the modularity. And the modularity tells you that you want to have a parameter psi such that the diagrammatic picture holds. And moreover, this psi should be non-zero. Okay. And then, so I mean, it's all these things need a proof, so I don't have time to give all the proofs, but I just want to say that roughly the idea is that you show that there exists a scalar, which is in C, which is in C, and you use the factorization property for transparent endomorphisms, and then some extra properties of M traces in order to show that you have a scalar. And then once you have a scalar, you want to show that this scalar is non-zero. And then in order to do this, you look at your picture, and then you close it up to the right-hand side with a trace. And then you can basically you can compute each bit by using the functoriality property. And then you using the form of the each piece, you can see that basically you get a sum of ones, and so it's not zero. Okay, but here it's a computation to be done, but that's roughly the idea. And now the theorem tells us that D is a modular G category relative to z2 times zr, and then x. Okay, so this is the way of constructing the modular category. But the thing that I want to say is that this G, which is used for grading, in other words, for somehow splitting the category, is extremely rich. So this G in this case is the whole H star, which is factored by the root lattice. And now in the next part, we will do something else. We will grade by something smaller. Okay, we'll grade by something smaller, and then yeah, we will use the perturbative modules for that. So that's the last part. So that's the fourth part, which concerns perturbatives. Okay, so once again, we have the perturbative weights, which were indexed by z to the power r-1 times c, because it was that condition that the weight evaluated on all h's should be integer, except hm. And then we will look at the set of perturbative weights, which we denote by c, which contains the weights lambda ac, where c is in n power r-1, and a is complex. Okay, so this c is basically just n times n power r-1 times c. Okay, and then we'll start from here, and then we will actually use a smaller part of the weights, and so a smaller part of the modules which corresponds to those weights. And more precisely, an important thing that we use, it's alcove, which I didn't know exists, which contains the weights with these conditions. Okay, so basically, when you add all the CKs from the first part and then from the last part, you want that both of them are smaller than L, the root of unity. Okay, and this alcove somehow puts some boundary, and then we will use that. And so now I just want to make a summary of what we will do. So it's basically, it has 3 steps. So we start from dp, which is a category of perturbatives. Okay. So basically, on this picture, the perturbatives are just given by vertical lines, where all components are natural. Here, the blue dots means that you are in the n times n power r-1. Okay, so we look at this blue part. That's dp. And moreover, you will look at a particular subcategory, which we call dbbar, which is a subcategory generated by, in some sense, standard modules. Okay, basically what we will do is to just use this set and then try to generate using that. So we start from that slice, we'll generate, that's dbbar, but somehow we still generate too much. And then the last step is to take a quotient. And then you will see that somehow on the picture, the quotient would mean that somehow you just look at this part, which is in the alcove. And then when you look at this quotient, show that that quotient has the right properties, and that is a relative pre-modular category. Okay, so there's 3 main steps, and then somehow you start from dp, use some of its properties, and then go smaller and smaller, and then get to the relative modular one.
And this quotienting is quotienting with respect to TP negligible. So this category DN is not semi-simple in the classical sense at all, right? No. Yeah. Yes. So we will see that.
So I said with the first part about dp. So one thing that we have and we'll keep on from now on, it's a grading. So we'll have a grading on dp, which is gp, which is c over z. So you see that this time the grading, it's a much smaller set, c over z, with respect to the previous one, which was huge. Okay, and now we see that in the grading z bar, we look at the modules such that km to the power l acts by this scalar. Okay. So the scalar which is the power u, such that u is a complex number which has the same class as z bar. Okay, so that's the grading, and then the critical set, it's 1 over 2z over z. So now on this picture, it means that basically the slices will be vertical. Will be, so sorry, not vertical, or horizontal. So you look at a point here, and you look at all the weights which have that coordinate on the c side. Okay, and then you have L to L and so on, and then basically the grading, it will be from L to L, because it was C to L U, the grading. Okay, so this is the C over Z grading, and the bad set will be given by L over 2. So it's a critical line, and then you have the others from L to L. Okay, so this is what we have. And then we have a lemma, which tells us that basically away from XP, so away from this particular grading, we are semi-simple. So if we take two complex numbers A and B, with the only condition that their grading, their classes in C over Z do not add in XP, then if you take V which corresponds to lambda A0, and then V which corresponds to lambda B0, that is a direct sum of typicals. And then with no multiplicity. Okay, so it's semi-simple, and it's semi-simple with respect to typicals. So the picture, it's again like this. So you have the critical line here, which you want to avoid. And now you take just two gradings, A and B. So the first component is 0. So you are for sure on the first line. And you take A and B. And now to this A and B, we have, for each of them, we have a module. Okay. And now if we tensor these two modules, then the result is here. And it's a direct sum of typicals. Okay, so this is what it says on the picture. Right, and then another lemma tells us that we have a trace on this typical ideal. So basically, if you look at the ideal which is generated by any of these V0 lambdas, so the idea is that all of them will generate the same ideal. That's part of the statement. And then on this ideal, there is a unique trace. Okay. Right. So these are the properties which will keep on for the rest. And now the second part is to construct a subcategory, dp bar, inside this dp. And then this subcategory is basically a subcategory generated by nice modules. So basically, this dp bar will be generated by, so except three main things which are not, which are fixed. What we use are all these v lambda 0 z. For z, a complex parameter, which is not in the bed grading. Okay, so we look at this horizontal line, and we take all the modules corresponding to those weights, except the ones which sit in bed gradings.
These standard modules, are these are like vial modules? Are these like irreducibles for generic Q that you, sorry, what is it easy to say what the standard modules are?
Yeah, so the standard model, it's a n plus n dimensional module, which it's n plus n, and I think it's yeah, it's related to the generic one. Yeah, but it's just one thing. Yeah. And then we have two one-dimensional modules, which are basically just to control the parity and then to control the ejection. This is the epsilon controls the ejection. Yeah. Okay. So basically, what we do is to take the subcategory in this category of perturbatives generated by this four representations, 4 types of representations. Okay, and the idea is that this category will inherit many properties from the previous one. Namely, it has a trace on the ideal generated by v lambda 0 for any A, because all A's will generate the same ideal. So we have a trace, and we'll have a C over Z grading. Okay, so basically we just this is just a subcategory, so it inherits a grading. Okay, and so now the idea is to yeah, so the idea is to make a quotient, and then but before saying how you make precisely the quotient, I just want to say the structural description of this dbbar, because that motivates why the quotient is really very useful. So the idea is that if you look in this dbbar, if you fix A such that A bar is not in the bed grading here, the objects of the category in grading A bar are of the same the following form. It's typical plus negligible, and the same in a minute what negligible is. Okay, so T means that it's a direct sum of typical V lambdas, or tensor by C bar, and N is negligible, as I said. Okay, and then for any AC such that lambda AC is typical, then the corresponding module is in dbbar. So basically, you can describe all modules which are sitting in generic grading in that category. Okay, so now the rigorous definition is that an object is negligible if it's in the ideal I bar generated by V lambda 0, and if the trace of an endomorphism is 0 for any endomorphism of this object. And now a morphism is negligible, F, if you can find a negligible object and two maps to and from it, such that F is a composition of those two maps. Okay, and then we'll denote by negligible from V to W to be the homomorphism which are negligible between V and W. Okay, and so now, as I said, having in mind this structural description, it means that somehow if we fix a grading, and then we look at what objects we have in our category, it means that what we have is a typical part, which we like, And then there are negligibles. Okay. And the idea is that in order to get a finite number of simples in each grading, because these are infinite, right? The idea is to basically just get rid of the negligibles. And if you get rid of the negligibles, what will happen, it's actually that we will remain in this part. So we'll remain in the alcove, that's the idea. And so the way to do this is to consider the quotient category, which is a purification of this dbbar, where we basically keep the objects, but then in the morphism spaces, we just quotient by negligibles. Okay, and the effect is that if we have a negligible in a direct sum, that negligible it's isomorphic with 0. Okay, so then this dn inherits properties, and it will be a ribbon category. We'll have a good trace on it, induced from the previous trace. And then we have the properties that we want. So we have a free realization, which is basically given again by z2 times z. And somehow it will be constructed using the previous realization. I won't say more than this. And then the bad set is still half integers mod z. Okay, and the lemma is that now we have finally generic semi-simplicity. In other words, for any grading which is not in the bad set xp, dgn is semi-simple with finite number of simples, which are described in this way. So basically, there are these strips which somehow end in the alcove, and then you just go for a finite number of them. And then if you move them on with a realization sigma, then that gives you a completely reduced dominating set. And the theorem is that the n, it's pre-modular, C over Z category, and it's relative to Z2 times Z, and then half integers. And then for SL21, we show that it's in fact non-degenerate, and then we have semi-manifold invariants. Okay, so I think I stop here. Thank you.
Let's everybody thank Cristina. Talks, questions for Cristina? So this, so for SL21, you have a 3-manifold invariant. Is it just technically more difficult for the more general case to prove non-degeneracy?
Yeah, for the non-degeneracy, yes, it's yeah. I mean, we conjecture it's true in general for SLMN. Yeah, but it's more tricky, and also we conjecture that it's actually modular. So not just non-degenerate, but in fact modular. But the technical part, it's yeah, it's still to be sorted out.
I see. So okay, so you don't know for sure if this extends to a TQFT, but it's a conjecture.
Yeah. Yes. Yeah.
Okay. And do you? I mean, I guess it's all conjectural, but do you anticipate you'll get new topological information from like about mapping class groups for the TQFT for SL21? I
mean, that would be very nice. I mean, so the fact that it's coming from SL21 is definitely interesting because it's yeah, it's a super group, but yeah, I think it still needs to somehow be solved, and then maybe see some practical computations with it to see what really happens. Yeah.
Thanks.
So somehow this invariant for 3 manifolds, it's so basically you have the WRT, and then you have this invariant from SL21. WRT is SL2 and then SL21. So that this picture is somehow the generalization of what happens for links. For links, you have the Jones, and then you have the Jones from SL2, and then links good from SL21. And then somehow this is a generalization for 3-manifold case. Mm-hmm. So in principle, it could give new information, but it's yeah, there's still things to be studied.
Thanks. Other questions for Cristina? I'm going to also stop the recording.